there, and then this goes there, and then I want, okay. You open, and you're there, and that definitely didn't type that well. I guess I hand wrote that.
There were 2 boxes. So, cool. If you want me to take this back down on Monday, let me know.
And we're going to there. Sweet. Okay. And the last thing to do is make sure I have this opened up and add this device so I can see the chat. Make sure the ability to have all this handy. That's one reason why I drove in this morning. Cool. All right. I did, but let's see what happened there.
Have a good week.
Okay, so we kind of left off with the Greek and specific weight and density, and then we're moving into where are we heading to? A little bit more with specific weight, viscosity, and that sort of stuff. And so anybody confused by last class conversation? No? Okay. All right. And I think we're good here. All right. So a couple things I want to do with density before we go. I want to cover something because I'm not sure I did this well. Is with density. Oops, there's an I in there. We want to. Now that would suck too. Yeah, why worry about that? Teams here, share screen there, and pop you back up. Come on. And I want this and that. You can go away, and there's that. Now can you see things? Yes, I can see it too. Cool. All right. So one of the things with densities, we already talked about the shape, but I don't think I did this, and it's worth the conversation that goes with this. So if we take a look at density and temperature, so minus 10, minus 5, 0, 5, 10, 15, and that would be 20, and that line needs to go over there. But if I look at this, and this is temperature in Celsius, and I also remember this was a great question that was asked of me at my PhD project defense, and it was one of those things, where is the water the densest? It's like, really? You're going to ask me that question? But they did. So if you take a look at density, and we're going to deal with kilograms meters cubed, okay, we are at 999.5. And there's no sense to my scale here. Is once you get it, you'll kind of get the hang of this thing. 998.5 and then 998. But at this point right here, this is 4 degrees Celsius, okay? And that is the densest point of water, okay? And there's some fun things that go along with that. But if we look at the rest of these, they're literally going to kind of do this curve like so, okay? And with that curve, this being the densest point, it begs the question, densest point of rho. Okay. With that, 1,000 kilograms per meters cubed, why 4 degrees? What's so special about 4 degrees? What do you know about water and how it behaves? Okay. Anybody else want to take a speculation? So, given the fact that water freezes at 0 degrees, what happens when water freezes? Okay. So here's the thing I want you to think about too, along with that. So if water freezes, why doesn't a lake freeze from top to bottom? Anybody ever go ice fishing? Anybody ever cut a hole in the ice? Okay, so the water's warmer below the ice. Well, that's an interesting little thought. There's some pressure there, but 10 feet isn't going to make a lot of pressure, and we haven't even talked about pressure yet with fluids. But yeah, it's not like we're diving down 90 feet and the pressure's different there. But there is pressure difference, but it's minuscule. Let's put it that way. Why does the ice form on the top and not form from the bottom up? There's a good reason why it shouldn't, but if it did, there'd be an awful lot of dead fish every year. It does, because ice does form an insulation barrier. Okay, I'll stop poking around here. But you guys are thinking about it. That's cool. That's what I was after. So there's this wonderful science called limnology, the study of lakes. And there's 3 outstanding volumes written by this guy back in the 1920s. And they're like the gospel of all books on water. But generally, this is what happens. So we tend to have water in the fall in a lake turn over. So we've been gaining heat into it all summer long. And you've ever been swimming in the middle of the summer and you hit a cold spot and then you hit a warm spot and you're not sure why? It's because how much energy is being absorbed, or the water is being stirred in different ways at certain points in the lake or the river. I know that because I spent a lot of time on the St. Lawrence River as a kid, and you really couldn't swim in it until August, according to the adults. But I was dumb and young, and I didn't care, and I went swimming, and it was 50 degrees, and you'd freeze, and you get out, and you're shaking, your lips are blue, and you're wondering why, but you go back in anyways. So all summer long, that body of water is gaining solar energy. If you take a look at this, as we rise in temperature, the less dense water is on the surface, and the denser water would be down below. Okay. But what happens in the fall is we wind up flipping the lake surfaces over. So basically, we get enough wind that's blowing across the lake, and it churns the lake. And when it churns all that water up, it puts the dense water up on top, and it reoxygenates the water, believe it or not, for the animals that live there. And then when it starts to freeze, it won't freeze when water is in motion. It freezes on a very still night without clouds, and it has to have the ability to radiate its energy off to outer space. So you'll get a thin layer of ice forming on a body of water when there's a clear night, and it can just radiate all its energies, and it just loses it fast. And that forms the layer of ice. Now, why doesn't the ice sink to the bottom? So I told you that water is the densest at 4 degrees Celsius. At 0 degrees, when it starts to freeze, where's it going to go? What's the density mean to you? Yeah, because it's less dense, right? So we literally, when we invert the lake body over and we turn all that water over, we take that dense water and we send it to the bottom of the lake, and the less dense water floats to the surface. And so things will move by gravity to their best advantage, and more dense stuff falls to the bottom, which is similar to what you do when you do what's the phrase in soils when you got not a dilution, you got water, soil, and muck in a solution, and it settles out. All I think is distillation. That's not it. That's that phrase. Well, it's similar to that, but there's that phrase where you put it in the graduated cylinder and you watch it over a whole week, and it the dense materials. Now, not the hydrometer analysis. Well, it is the hydrometer analysis, but the muck, the soil, and all that stuff is settling to the bottom. All the silt goes to the bottom. Why? Because it's more dense than the water is. But when the water has it in solution and it's been agitated, it moves with the water molecules. And it's still... So I guess what I'm trying to get to is that less dense water floats to the top. The denser water, being heavier, floats to the bottom, or sinks to the bottom. Actually, doesn't float to the bottom. And so we wind up forming that layer of ice. So water density is an important thing from the standpoint of what we're able to do with the fluid. Okay. So as we warm up in the summertime, we start going over into this area here, and we have less dense water. But then we come back to 4 degrees. There's still a magic little principle about 4 degrees that I'm not sure I've ever gotten right, other than I just memorized it and just know it's there. But it's the point where the molecules cannot come together any more than they can. So you think about the units on density, kilograms per cubic meter. So at its densest point, it's all I can do to squeeze those molecules together, and I can't get anything closer to get more mass into that volume. Does that make sense? And then when I start heating it up, it expands so that it becomes and fills less mass per volume. But then when I go the other way and I go below freezing, it's why ice floats, because ice is less dense, and the molecules that form ice actually spread out into the larger volume, so the mass is less in a larger volume. So if you ever did this experiment, get a glass of water, throw some ice in it in the summertime, mark the side of the bottle or the glass with a marker, watch the ice melt, and mark it on the glass again when the ice is melted. You will notice that the water didn't change level one bit, because the volume that was taken up by the ice cubes have now dissipated into water and replaced the volume that the ice cubes pushed out of the way. Make sense? Cool. All right, so that's probably way more information that I usually give out, but it's my lecture and it's our remote day. So, all right. Okay, I know I said specific weight, but the next topic we're going to cover is specific gravity. And this, if you've done soils and done that hydrometer test, you know what this is about. All right. I got to sit up close here. I can't sit. Okay, so when we measure specific gravity, we're actually checking one fluid against another. And the cool part about this is water has a SG equal to 1. Okay? So we can look at this, and the equation is this. The density of a fluid against the density of water at 4 degrees C. Okay? And when we're all said and done, there are no units on this. Okay? So you could wind up with a SG equal to 0.9. You could wind up with an SG equal to 1.3, depending on what the fluid is. Okay? And the cool part about that is it also explains why oil floats on water and you can never really get the two to mix well. Okay? So if you're into making your own salad dressing, you usually add water, vinegar, and oil, and it's because the vinegar and the oil will help break the surface tension of the water, and you can actually get it all to shake up. Okay. Plus, it adds the flavor to it. But generally, we can look at things one fluid against another. So you can get you're actually going to have some homework problems here soon that have an oil of 0.83 or something. What's the density of that oil? Well, if you know the density of water at 4 degrees C is 1,000 kilograms per meters cubed, you can figure out what the density of the oil is. So, anyways, everybody okay on that? Cool. And if I keep talking and forget to stop and ask if everybody's okay, somebody can holler at me. I'm skilled at doing remote teaching, but I've forgotten how to do it effectively since the pandemic because it's so much easier to look at y'all and go, hey, I see a deer in the headlight look. You're not getting it. Okay, so specific way we covered, I think we did. I may be rehashing some stuff, sorry. I think I did, didn't I? Oh, I know the other thing I should do, just to make the world a happy place. When I do volume, I draw a line through it because there's a whole lot of times where we got V for velocity, and then we got V for velocity. And if I do this, I'm looking at volume. And the National Plumbing Institute or National Society of Plumbers or something like that, plumbing engineers, basically got sick and tired of people getting the symbol wrong. So if you see a V with a line through it, think of it as a glass half full, and it's volume. Okay. So we covered that one, so I'm not going to hash that out anymore, other than remember that is unit weight. And I want to get into viscosity next. Yes, I do. There's specific gravity. And we're moving in the right direction here. Other than I got to change the title on my page here. So viscosity, it's another principle of this. And I think the easiest way to do this, I was just going to do a problem for you so you can see this. But it's the, I defined this, didn't I? Or maybe I didn't. Oh dear. That's the problem when you stop a lecture halfway through. And did I define viscosity? No. Yeah, okay. Viscosity is the So it's to measure the resistance to shearing. So you hopefully remember from either Strength of Materials or someplace else in your life around here what shearing is, right? Anybody not remember what the shear stress is? Cool. Silence. I'm going to take that as consent that you remember it. But here's how we measure this. So we literally start with two plates like so. We have a plate down here. And this plate is going to be fixed. Okay. And we have a difference of 1 millimeter between the plates. And then we're going to take this plate and we're going to give it a force. Actually, I'm just going to use F equal to 0.001 newtons and a velocity equal to 2.9 meters per second. Okay. And inside here is a liquid of specific gravity equal to 0.73. Okay. And literally, we're basically taking this plate and going that way with it while this plate stays still. So the fluid, oh, cool. I get to use different colors today. Let's use blue. So the fluid here is at 0 velocity. Okay. But up here, we're at 2.9 meters per second. Okay. So literally, if you think about that, it's like sliding that sheet of paper or a ream of paper, top sheet forward at 2.9 meters per second. The bottom one stays attached to your hand. And you wind up creating that little staircase effect. And if you think about it, all that fluid is going to try and do the same thing. Okay. So if I zoom in here for a bit and we play a little games, I got there, I got there, I got there, I got there, and I got there. So anybody taking differential equations yet? Yeah, they talk about streamlines in there. Maybe, maybe not. Maybe that's another math course and I'm getting my classes screwed up. But streamlines basically came from fluid mechanics. And it's one of the things I spent a lot of time at grad school dealing with was understanding the streamlines. But if you think of the molecules in water, at each molecule, one's going to move a little faster than the one below it. And the one below it will eventually get to the point where it's attached to something and it doesn't move at all. So we literally get, in this case, we have a profile that literally does this on the fluid. Okay. If we started there, we tip it forward into a triangle. Now, it doesn't actually move in a nice straight linear path because nothing's that nice in nature. It's probably more like a parabolic curve where the bottom is real. Well, you know what a parabolic curve looks like. I'm going to draw it. Where it starts here and kind of goes up like this. and it gets to the point where it's all uniform. Now, the cool bit is that happens when we're dealing with open channel flow down the road, and we're trying to understand where the scouring effect is and how much is going to be taken away, or where it's going to be slow enough to drop the sediment out of the water. So things like that. Cool. Now we have a couple different things we got to find here. So I'm pretty sure I defined this the other day, or maybe I gave you the Greek letters for it. So dynamic viscosity, and that was mu. Okay, so just a reminder of that. And then we're going to go find kinematic. And that was that goofy looking V thing. Okay. And our equations for this are mu is equal to tau times the displacement times the velocity. Okay. Shear stress divided by change in height over the velocity. Okay. And then to do that, sorry, I've been talking too much today. Sorry. Tau is the force over the area. And in this particular case, I gave you a distance or a force of 0.1 newtons. And we're going to get away with a 0.1 meters squared. And that was based on the... where did I give that to you? Maybe I didn't give it to you. Anyways, I'm just going to pick a plate that is that thick, or that's the surface area of the plate. And we're going to get our answer is 0.010 newtons meters squared. Okay. And that looks somewhat familiar, but it's still not the answer to the whole thing. So we come back into our tau and we put 0.010 Newton meters squared, and we're going to multiply that times 1 millimeter. And because we are in meters, we need to do a conversion table here. Okay, and I need to straighten out that. And our velocity was 2.9 meters per second squared. And when we get all said and done, oh yeah, I got nope here in my notebook. Do this right. Yeah. All right. So we get an answer of 3.4 times 10 to the minus 6. And these units are Newton, seconds, meters squared. Okay. And it gets really ugly with conversions of all this. But if you're interested someday, remind me and I will pull them all up and actually do the calculation. But a Newton meter squared is what? Anybody remember? What do we call that? Yep. So literally, we define this in terms of 10 to the minus 6 Pascal seconds. Okay. So that's your kinematic viscosity, or your dynamic viscosity. Sorry, I was thinking ahead of the next problem. Now let's do your kinematic. So I don't like that. Okay, so that's your dynamic viscosity divided by your density. Okay, and we had specific gravity of 0.73 up here. So I'm going to go play with that. So first thing I got to do is find out the density of that fluid. Okay, and it's a specific gravity times the density, and I've used a W for water in this case. Okay, 0.73 times 1,000 kilograms per meters cubed, and I get an answer that comes out as 730 kilograms meters cubed. Okay, so that's our density for that particular, I'm not sure if that's an oil or what it is exactly, but all right. So now let's go find our viscosity for kinematic. And we get to plug in the 3.4 times 10 to the negative 6. I'm going to go back to the other units here so we can make some units disappear when we're done. 730 kilograms meters cubed. So sometimes in this world it's easier to keep the units so you can see things cancel out. So anybody remember what's in a Newton? Okay, remember that's equal to a Newton. So when we get all done, the kilograms will cancel out. Our meters will start knocking themselves silly here. When we get all done, we wind up with 4.73 times 10 to the negative 9th meters squared per second. So if you see numbers that come out with weird units on it in fluid mechanics, it's probably the kinematic viscosity. If you find something that looks more like normal stresses and seconds and time, you're dealing with dynamic. That makes sense? Cool. Everybody follow the math, or anybody confused or lost? Okay. Cool. All right. That was that example I just did. And we're having fun now. Well, I'm having fun. I don't know about you guys. All right. Okay. Here's one for, who said woohoo? Oh, okay. All right. So here's one for you guys to give a shot at. Normally I just put this on the board and let you guys work it out. But so get yourself a piece of scrap paper. I'll give you enough time to do this. But here's a practice problem. And I got to be careful not to give the world away here. All right, let's do this. Given a liquid, All right. So that's the problem. You guys got a little bit of time to play with this one. But what I do, I threw in some really fun stuff related to the specific weight. So no density in there. And I've given you I've given you the dynamic viscosity. I'll tell you that up front. So ideally, we're not looking at a whole lot here, other than we got to come up with what the density of the fluid is. So I'll give you that much hint. Okay. And if anybody's got any questions, just chat up and tell me what the problem is, and I can help you. Give you about 4 minutes to take a whack at it. Other thing is, Dr. Regal, I need to make sure the homework assignment's there, but I probably should go in and scan the question page out of the electronic book and put it up in there. So, okay. Yeah. Things out we don't have any textbooks because $200 for a book that's out of print. Yep. Yep. Their work into the Dropbox. Okay. This is hard to look around the room and not see anybody working. I just so desperately want to do the problem. So all these parts and pieces you've seen so far, this is probably the first, well, I know this is the first one we've done any math with, that is finding the density, but now there's a question. Let me ask this question. Maybe I didn't do this. I don't know what I did on Wednesday, let alone what I did 20 minutes ago. You understand that the density of a fluid is the specific weight divided by gravity? Does that help anybody? Cool. And then the only other headache I threw in there at you is I mixed units intentionally. Is everybody seeing it? I mean, I don't want to take all your time or take all your time up, but I got about 5 minutes now to do this solution for you. Is everybody okay if I start, or do you want me to give you some more time? Okay. Cool. All right. So, step one. Find the density. And we're going to do that by, I guess I have to keep my rows consistent here. Gamma divided by gravity. And I gave you this 56.3 pounds per cubic foot. And what you need to remember is there's 4.448 newtons per pound. And then our feet is 1 foot divided by 0.3048 meters. And then we're going to cube that. And we're going to divide it all by 9.81 meters per second squared. And we're going to wind up with 901.5. 5 Newton meters cubed divided by meters per second squared. And I don't want to mess with that yet. I know technically we should take that 1 meter and make meters squared up there, but we want to be careful. We don't do something crazy yet. All right, so we know, what do we know? We got to get that times 1 kilogram meter per second squared divided by, I never make these things long enough, 1 Newton. All right, and that'll get us our conversion to 901.5 kilograms meters cubed. Okay, and then we can go find number 2, find our kinematic, I guess I should write the word find, proper engineering setup. And we're going to do this. The density of the fluid, and 2.10 times 10 to the negative third kilograms meter per second divided by 901.5 kilograms meters cubed. And we get all done. Just to make life simple, I'll stick with the right here. 2.33 times 10 to the negative 6 meters squared per second. And that is our final answer. Okay. One other thing too, as long as I'm doing this, normally if you got a piece of computation paper, you literally have a line that runs down through here. No, not that one, that one. Got a line that always runs down through the outside like this before the edge of the paper. It's always a good idea to stick your units out here so that you know if you ever have to come back to something and you got a lot of sheets to flip through, that you can find the unit that you actually did the work on. Okay? I don't know if anybody's ever told you that or not. Silence. I'm going to assume they did. All right. Questions on this other than a few little things to look up, and you got to remember some basic conversions, that sort of stuff, but it's not impossible to do. Okay. That reminds me, I should check on the Brightspace site to make sure that I put the unit conversion stuff that I had up for you guys to have. So if not, I will do it. So there's that, a little note to myself. All right. Any questions? All right. So, cool. My question is this. How many have given homework already in the faculty, and do you have time to do this? I think there's like 4 problems for Monday, or do you want some more time? Okay. So I got one for Monday. Cool. All right. The reason I ask is so I'm the one that everybody comes to complain to when the faculty start giving too much homework out and you guys can't get it done. Um, I get it from both sides. I get it from the students who go, well, I couldn't get it done because so and so had this much homework too, and they did this one over here in this class. So if you get to the point where I'm going to assign something to you and you think you're not going to have time to do it, I'd rather give you a little extra time to do it than to fight against everybody else's workload. Okay? So you help me, I'll help you. Oh, by the start of class is usually a good time. That way, if you got any questions, you can bring them in, and I'll try to answer them for you. Yeah, that's probably true. So midnight on Monday then. Yeah, because you're all up at midnight. You know, the faculty all go to bed by 9 o'clock because they're worn out. Oh God, if that was only true. I've actually remember helping students at like 10 o'clock at night because I was still doing something on the computer. And it's like, oh, I might as well answer it now. All right, that's the lecture for today. We are going to be doing a lot more math, so you might want to get your calculators warmed up, and I'll give you a chance to ask questions along the way as we do it. But we're starting into the fun stuff now, so no more terms and that sort of stuff. Just a lot more concepts and the math that goes with it. All right. Any questions? All right. I'll have that up here in the next hour, hopefully, and I'll make sure I got the unit conversion worksheet up that I have so that you got all that stuff too. All right. See you all on the flip side of Monday. Okay.